Okay, about DNA replication, I think the first thing that we want to focus on is looking at a picture that's like this. And yeah, that's drawn pretty poorly. Whatever. If this was 5 prime, what would this then be over here on the bottom, right below it? Okay. And then this would be 3 prime right there, and this would be 5 prime right there. Okay. Now you can see here, but let's show the way. You can kind of gauge that this black line that I've drawn here is like the original strand, correct, or the parent strand. And if this was a T right there, then there would be an A right here. If this was a G, this would be a C. Hydrogen bound right there. I could follow this principle, but I think you got it, correct?
Like those two lines of
No, they're the same color. I'm showing you the black color that we have here is representing the parent strand. The original strand, the strand that has not changed. What is this area called right here? Okay. The same would go with this area over here, the replication fork. Now, there's been some enzymes that have been involved in assisting you in like allowing this replication fork to exist. Right here, actually, I would call this a replication bubble. And some of the enzymes that we've used, at least by this point, would be helicase, SSBP, and topoisomerase. What's the value of topoisomerase? What does it do? Or I'm sorry, of helicase. My bad. Do it? Unwinds. Unwinds the DNA. It also disconnects the H bonds between the bases. SSBP stands for what? And this is gonna like help maybe like keeping the two strands apart. And what about topoisomerase? What does it do? It prevents like an overwinding or a rewinding or an underwinding. If you think about it, if you were to unwind this region that I'm kind of pointing to right here, that would mean that this region up ahead or well back behind could actually start to wind up like pretty significantly. And you could think about like a wire, like if you had a wire that was wound up, and you like unwind this section, then you would cause the sections right through here to be even more wound than they were originally. So it's that concept that I want us to focus on. Cool. And we do see with the 5' and the 3' ends that the two strands are anti-parallel, so they run the direct opposite directions. And so the next thing that you would do is you would talk about like which ways that you would add in these new nucleotides. And the big enzyme that I want to talk about here, there's actually two enzymes. I want to talk about primase, and then I want to talk about the role of DNA polymerase. Does anyone remember what DNA polymerase is doing? It's what adds new DNA nucleotides, one by one. And primase, what does it add? I think I heard someone say it. Adds RNA nucleotides at the beginning. So at the start, it adds the RNA nucleotides. Now it makes sense that the replication fork is going this direction. You see this like left-hand direction that it's going there, and then you see the right-hand direction that it's going over there. And it seems logical that if this is a 5' end over here, Then this new strand that I could draw in right through here, what would this side be? 5 prime? And this would be 3 prime. So there's no problem adding bases going this direction. Adding them one at a time. Now remember, those first couple of bases are going to be RNA primers. The rest of them are going to be DNA nucleotides, though. What would the end? What would this strand be right here? This end. It'd be a 5 prime, and this would be a 3 prime. You realize that that would allow this strand that I just drew in red, this new one, to run anti-parallel to its complementary strand that it's going to be attached to when this process ends. What type of strand would this be? Would this be leading or lagging? Which one? Because I'm hearing leading and I'm hearing lagging both. It's leading strand.
Can't you only like add it to the 3 prime end?
That's right. So you would be adding to this end going this direction each time without fail. Question?
Could you explain why we lead?
Because the 3 prime end is on this side. You can only add to the 3 prime end. Now, I'm gonna let's do a little different question real quick. Let's do geometry. Let's say that this angle right there is 70 degrees that I just drew in. Tell me another angle. Correct? And that would be both of them because the rules are supplementary, right? What is the angle that's on the opposite side? 70. So we understand this principle of just geometry, correct? That was back in the day? Okay. I go over this and I say this. Easy. Cool.
Easier than the last one. Can I say that right?
Thank you.
I read over it.
Awesome. So you know how like in geometry, once you have one, you know them all? Leading. Leading. Lagging. Lagging. Cool. So that would mean like on this one over here, when you're doing this principle, can you just simply add going this direction? No. So what you have to do is you can envision that the new complementary strand that will exist is going to go that direction, right? So what you do is you come to the replication fork, you start and produce segments so that you end up with all these little segments that look something like this. What's the name of those little segments? What are they called? Okazaki fragments. I'll get it. To assist us with this, you can realize there would be fragments here and there would be just one straight line right there, so I'll do the straight line. And then I'll do all these little fragments going this direction. Fragment there, fragment there, fragment there, fragment there. Cool. Now you need a couple things. One is you need the RNA primers that were added initially at the beginning. You need them to be like yanked out. So you would need you need something to cut, right? Some DNA. And then you need something that could glue some DNA. So who's the gluing agent here? Perfect. So it connects or glues neighboring nucleotides together. Cool. And then there's also nuclease, which works to cut out certain nucleotides. What do we think? Does this seem pretty good? Awesome. I have a video over it. Do you want to watch it, or
Yeah.
Sure.
fun video? Okay. I think this video is also on the website. Pretty sure it is. It was like back in the day.